Good evening and welcome, everybody. Let's wait for one or two other people coming in. Welcome to this exciting event with Chris Lintott in particular. The Royal Society is the UK's National Academy of Science, and it's always great to have people here and to regard it as something you can pop into. Tonight we've got a very, very special event, but before introducing it, first of all, I'll say who I am. I'm Alex Halliday. I'm the physical secretary of the Royal Society. We have a biological one in case you think there's a virtual one. The other, I'm the physical one. Please, can I ask you to switch off your mobile phones if you'll put them on silent. There are no planned fire evacuations tonight. So if the fire alarm does go off, it's real. And you need to head out through these exits here or the ones at the back, whichever's easiest. Just lastly, I'd like to remind you that this evening's event is going to be webcast live and recorded for the Society's archives. So that will include the questions at the end. So if you don't want to be caught on a webcast, just to warn you, the stuff's going to be on. Okay, so tonight we've got with us Chris Lintott, who is Professor of Astrophysics at Oxford University. He read Natural Sciences as an undergraduate at Cambridge, and then did a PhD in astrophysics at UCL, focusing on the problems of star formation. Chris has long been heavily involved in science communication on the television, in books, and on the web. Today we have been at a meeting actually organised by Sally Shuttleworth, who's there in the middle, and her team here at the Royal Society, with historians, publishers, and other scientists to discuss transformations in scientific publishing and the relationship to citizen science. Currently, Chris is co-director of the programme on computational cosmology, and he's the citizen science project lead in the Department of Physics at Oxford. He was director of citizen science initiatives at the Adler Planetarium from 2010 to 2012. Prime Minister David Cameron appointed Chris as astronomer trustee of the National Maritime Museum as well. His research focuses on galaxy formation and the application of astrochemical models of star formation to galaxies beyond the Milky Way, particularly the use of sulfur compounds as signatures of stars that are in the process of formation. Chris first appeared on the sky at night in 2000, and he gradually took on a more prominent role as Patrick Moore became less mobile. Since 2012, he has been presenting the programme along with others following the death of Patrick Moore, who had himself been presenting since 1957. At Oxford, Chris co-founded Galaxy Zoo and subsequently established Zooniverse, about which I guess we're going to hear tonight. In 2011, Chris was awarded the Royal Society Cone Award for his excellent engagement with society in matters of science and its societal dimension. In 2014, he received the Beatrice M. Tinsley Prize from the American Astronomical Society for his insight and creativity that created a transformative approach to science by engaging non-scientists in cutting-edge research. Tonight, he's going to talk to us about science with a million people. Please welcome Professor Chris Lintott.
Well, thank you very much. It's always a pleasure to be at the Royal Society, although I see from the boards outside that you've abolished the Cone Award, so I hope I didn't break it after you kindly awarded it to me. But thank you all for coming on a Friday night at a busy time of year. Don't turn your mobile phones off. We're going to be using them at various points during the lecture. For starters, if you haven't answered this question using the instructions on your seat, you have probably about a minute or so to do so. So please do. Sorry? There's a piece of paper. Yeah? You good? Doesn't absolutely require you all to do so, but it will be important later in the lecture. So that I just want to check that the system works. And what I'm going to be talking about is, as you heard, the process and the ideas and the stories that have come about through citizen science. And for me, that idea started as a desperate attempt to get other people to do my work for me. We had 1 million images like this one. Most of them had never been seen by people before. They'd been automatically captured by a telescope, recorded and sorted. I'll show you some more of them in a second. And we need to work out what shapes are revealed by these images, because they tell you about the history of these galaxies. And so we found that by asking simple questions, like the one at the bottom, is this a spiral galaxy, an elliptical galaxy, or something else, we could engage large numbers of the public in this very simple scientific task. But in doing so, we produced data that was actually helpful to us. So if we could switch to the results screen, let's see how you did. Hey, excellent. The system works. That's mostly what I'm happy about. So you see there's a vast majority think that the picture that we were just looking at was a spiral galaxy. Well, if we go back to it, I can see why you think that. The central galaxy is indeed a spiral. I picked C, something else, because the spiral is actually merging with this neighboring galaxy, but I didn't give you enough information to work that out. And so one of the things I want to establish early is that although this is a simple scientific question, deciding what question to ask is important and critical and tricky. But I think that's a pretty good result for crowdsourcing. So the system works, and we can do citizen science. Of course, this idea that the public might want to get involved in science is not a new one. It's a very old idea, and the project that I'm part of, Connecting Scientific Communities, which is funded by the AHRC, looks at the connections between the modern practice of citizen science, the sort of galaxy classification and other things that I'll be showing you tonight, and the 19th century beginnings of volunteer involvement, a time when amateur paleontologists found things like this in the beaches around Lyme Regis, when meteorology was the domain of a scattered band of amateurs recording rainfall records and keeping an eye on their own weather stations, and when astronomy, then as now in fact, was the domain of amateur astronomers with large telescopes keeping an eye on clouds on Jupiter, discovering comets, and exploring the behavior of stars. And so there's this old idea, but it underwent something of a transformation within the 20th century. When I was growing up as a small child, I was a small kid with a telescope, the kind of thing that you could plonk down in the back garden in my suburban house where I grew up, and I desperately wanted to discover something. I'd been inspired by these stories of 19th century amateurs, and I wanted to discover pretty much anything I could find. Top of the list was a comet. Comets are named after their discoverers. Comet Lintott still sounds pretty good, but I would have taken anything. And the closest I ever got was this thing. At the bottom, you can see some nebulosity, some glowing gas. That's actually the top of what's called the Orion Nebula, our nearest stellar nursery. And I enjoy looking at the Orion Nebula. If you look in a small telescope, it's one of the few objects in the deep sky that really looks impressive. You see this three-dimensional structure of this gas wrapped around the glowing hot stars that have just been born. And so I can look at the Orion Nebula. I did look at the Orion Nebula for hours, I still do. But on the one particular evening, I nudged the telescope, and it moved upwards, and it revealed this cluster of stars. Now, this was a time before I had the internet at home. For the younger members of the audience, this meant we had to rely on books. Books are like the internet, but they don't update, and they're kind of small and papery. I get laughs from the publishers for that one, that's good. This is a way of identifying the various bits of the audience. So this cluster was not on my star map, the printed book I had at home. And I remember really clearly taking a pencil out my pocket and marking it on the star map and calling it Lintott 1. And that lasted till I got to the library the next morning and discovered that it had been discovered in the 18th century. It's called NGC 1981, which is a worse name. But I remember that was the moment when I realized I wasn't going to discover anything with a small telescope. I realized that astronomy in the 21st century was done with big telescopes, big professional facilities like this one. This is Sloan. This is a big survey telescope. It actually took the image that you were classifying earlier. And for 8 years, this facility in New Mexico allowed the sky to pass over it. It recorded the position of about 300 million objects, and 1 million of them were identified as galaxies, as distant island universes, systems of a few 100 billion stars. And on the clearest of nights, the telescope went back to those galaxies and it recorded their distance. So we have a three-dimensional map of 1 million of the nearest galaxies. And so that's the data that I work with. We're going to fly through it. starting on the Milky Way and travelling outwards. And you'll get a real sense of how far we've got in mapping the universe. This is about half the data, so I've got about 500,000 galaxies in here, and a few tens of thousands quasars, distant galaxies. So each dot here is a galaxy, hundreds of billions of stars. First thing you notice, I think, is that space is pretty empty. There's lots of space between the galaxies. But as you get further out, we find this slightly remarkable thing, which is that the galaxies aren't organized randomly. There are places where there are loads of galaxies in the universe, and there are places where there are very few. In fact, this has a honeycomb structure that we tend to call the cosmic web. And so the idea that there is structure on the largest scales that we can reach in the universe is really surprising and requires explanation. Ignore the big stripe down the middle, that's just because of the way the survey was set up. But the structure on either side is real. And in a minute we'll stop and we'll rotate the universe for you. No expense spared. And you'll get a real sense of this sort of three-dimensional structure. There we go. The fact that it looks like a bow tie is just an artifact. The gaps in between the halves of the bow tie are the equivalent of here be dragons. They're the bits of the universe where we haven't filled the map in yet. But again, the honeycomb structure is real. And the game we play as astronomers is to take large computer simulations of the universe, to try and match those computer simulations to these observations. And if you get a good match, you can be reasonably confident that the physics that you put into the computer simulation matches the physics in the real world. And the problem is that, to first order, our first guess at doing that is pretty good. We have a model of the universe that works, but it relies on putting 96% of the energy in the universe into forms of matter and energy that we don't understand. So this is either an excellent triumph, our computer matches reality, or a dismal disappointment because we only understand 4% of the universe. And in either case, what we need to do to make progress is to find new ways of interrogating this data set, of asking questions about what we've seen. And one of those is the question I introduced at the front. Previously, people had treated these galaxies as if they were all the same. They are blobs of matter with a particular mass. You can measure the mass. But all of these galaxies here have the same mass, the same number of stars roughly in them as well, and yet they each look very different. There are spiral galaxies, there are ring galaxies, there are warped disks and mergers, including the one we classified together earlier on. By the way, somebody said they'd bring me a laser pointer, and I don't have one, so if there is one around, that would be great. I can wake people up in the audience if I have one of those. So the shape of a galaxy is this extra piece of information. It tells you about a galaxy's history, because the shape is affected by everything that happens to the galaxy and its stars. So the shape of a galaxy tells you whether it's collided with other galaxies. It tells you where and when it's formed stars, and it tells you something about, blimey, it tells you something about whether it's taken on gas from its surroundings. The problem is that computers aren't very good at this sort of fuzzy pattern recognition. So it's very hard for a computer to learn how to differentiate a spiral from an elliptical galaxy, a task which most of you did very well with no training or context whatsoever. So this is a place where human pattern recognition works very well. That's okay. I'm in a university, I'm an academic, so we have plenty of humans around. So we gave this task to a student. The student's name was Kevin Shawinski. And the first result of Kevin's thesis was that a student will do about 50,000 galaxy classifications before he tells you where to stick the rest of them. I'm translating a bit, that wasn't quite what he said. And so I tried buying Kevin beer, but that didn't work. He still refused to go through the other 950,000 galaxies. And so in desperation, we created this website called Galaxy Zoo that gave you one of these galaxies, asked you whether it was a spiral or an elliptical. If it's a spiral, we wanted to know which way the arms were going. If you're curious about why, ask me at the end. We had a merger button to deal with the ambiguity we had at the beginning, and a button for any stars that worked through. This worked brilliantly. Hundreds of thousands of people took part. Over the history of Galaxy Zoo, which has now been running for about 8 years, we've collected about 300 million classifications of galaxies. That means I've had lots of people look at each galaxy and taken collectively their results are excellent. So we can now split our galaxies into ellipticals and clockwise spirals and anticlockwise spirals and so on. And what's more, I actually have more information here than if Kevin had done all of these on his own. Not only are the crowd more accurate than Kevin, when he was doing his 50,000, made mistakes. It's natural if you're doing one person doing tasks, but if I have 10 people look at each galaxy, collectively we don't make mistakes. But I also have some information. For example, my guess is that 10 out of 10 people would have said this was a spiral galaxy. But maybe only 6 out of 10 people said that this was a spiral galaxy. And so I have not only a classification, but I can estimate my confidence in that classification as well. And that turns out to be hugely useful. And so Galaxy Zoo was the first such project to really have a scientific impact, but it demonstrated that there were hundreds of thousands of people who were willing to give up spare time on the web to help scientists do these kind of tasks. And secondly, it demonstrated that collectively people were pretty good. They could outperform computers, could actually outperform a single expert as well. And so this leads me on to penguins as the obvious natural step for this talk, because it turns out this problem of having too many images to classify is not an astronomical one. This is a problem that's shared by lots of scientists. And in particular, it's a problem shared by my mate Tom Hart, who's in the Department of Zoology in Oxford. And while sitting in the pub one day, Tom and I were talking, he was explaining that he used to go to Antarctica once a year and go and count penguins. Penguins are particularly sensitive to climate change, so it's kind of interesting. They have other interesting features as well. You can tell I'm an astronomer talking about this stuff. They're almost as interesting as galaxies, I think is what I'm really saying. But Tom used to do that, and that was his data set. But now he can buy a cheap camera for maybe $100. Use dollars because these things were developed first for lazy hunters in the States who like to put in their own backyard, very large backyards, would put out cameras so they could tell when there's an animal there to be shot. But these cameras are cheap, they're robust, they even survive an Antarctic winter. So now Tom goes to the Antarctic, carpets his study sites with cameras, and comes back a year later to pick up somewhere between 3 and 5 million photos of penguins. And this is fabulous, because not only does he have more data, but he can now see what happens to the penguin colonies when he's not there. He can work out when they arrive to nest, when they leave, and cover the whole season. But to do that, he has to work his way through 5 million images. So, simple question. How many penguins are there in this image? Somebody shout out. 3. Anyone want to say anything different? There's usually a computer scientist who says 2.4. Or some such, but 3 is the correct answer. 3 is the answer that Tom is looking for. Now you're warmed up. I told you this was going to be interactive. Let's do another one. So I want you to count the penguins in the next image and shout out when you've got the number, okay? Ready? Go. Anyone? 9,000. That's a good estimate, but this is exactly why it helps to have people. Because if you're a computer and you've been trained to count penguins on images like this one, when you go to this one, you give a nonsensical answer. Whereas if you're a human, sometimes people just say a large number. 9,000 is probably a reasonable guess. The point is you shift modes. You have that human ability to switch from what you've been trained to do to a different task. Normally people shout many, right? Which is also a correct answer here. But actually this is a rare image. Tom should not have put the camera here. This is sort of typical. And so using the same software that we used for Galaxy Zoo, we can build Penguin Watch, which is a website that lets you count penguins for science. Original name of this website was Penguin Hunters, but Tom and his colleagues wouldn't let us get away with that. But I highly recommend Penguin Watch. We've counted, I meant to look at the numbers, we've counted something like 5 million penguins in the last 3 months. And there are still plenty more to do. And so the point here is that this methodology that we stumbled upon for doing astrophysics is very general. And we have a platform called the Zooniverse, which supports about 50 of these projects. And if there are scientists or researchers in the room, it makes it very easy to launch your own project. There's now a web-based tool that lets you do that. And it's not just scientists. As a part of the ConSciCom project, which is the sponsor of today, we launched a website called Science Gossip. It's a very meta project. It's a citizen science project to help understand how people in the 19th century communicated science. And so it's named after a periodical. There was a journal called Science Gossip in the 19th century, which I desperately want to refound, because I think the title is wonderful. But the point of Science Gossip is to look at illustrations. And so there are wonderful things like this. I found this morning when I was looking through. This is from Science Gossip. There's a couple of reconstructions of dinosaurs. And we even have people in the 19th century. Oh, this is a bit blurred, but this is somebody writing about citizen science, or what we would call, it's actually an attempt to, as a report of a meeting, to decide how to complete the history of Wiltshire. My favourite bit is it says, the undescribed part of Wiltshire is not so frightfully large. But it goes on to point out that if one person tried to do this, no one at the meeting would live to read it, because it would take more than 100 years. But if you split this task up amongst a community, you can get more done. So we have a citizen science project looking in 19th century journals, finding descriptions of what we might call citizen science. And there is, in fact, this long history that I spoke about, which I'm going to just skip. So, I hope I've convinced you that citizen science is useful. We can count penguins, we can do galaxies, we can do history, and we can do many other things. But there's another feature that we find common across all of our projects, which is the ability of people to make serendipitous discoveries, to go beyond the task that they've been allocated. So I have three possibilities. I can tell you about Hannies Vorwerp, which is a giant gas cloud discovered by Galaxy Zoo volunteers. I can tell you about aliens, although note the disclaimer, or I can tell you about what we found in logs from naval ships. So if you've got your phones, please vote. Can we put up the results so we can have a live tally? This is very technologically exciting for me. Hopefully this will switch. So it's A for Hannies Vorwerp, B for aliens, and 3C for naval ships. Wow, I thought aliens would win. Oh, wow. There we go. I'm going to call that a stable response. So, naval ships. I really thought aliens would win. Never mind. Okay, hang on. So, we have a project called Old Weather. It's actually one of our oldest projects, one of the first things we did after Galaxy Zoo. Old Weather is a collaboration between the Zooniverse, who provide the software, and the Met Office, who are interested in actually a rather similar problem to the one that we had when we were dealing with comparing our observations to computer models. We have computer models of the cosmos, and we want to compare to our modern observations of galaxies. The Met Office have extremely powerful computer models of the climate, and they want to understand how accurate those models are so that they can predict the future. In cosmology, in astronomy, we can't run the universe again to get another experimental data set. The Met Office don't get to run the last 100 years again and again and again to compare their model. What they do get to do is use historical observations to understand how well their model's performing. In other words, they predict the past to understand how well they're going to predict the future. And they're limited in their ability to do this by the quality of the data that they have about the past. For the 20th century, at least since about 1920 onwards, they have good data about the whole world. Before that, it gets very spotty, especially outside Western Europe and the eastern seaboard of North America. There are only scattered weather records, and so that allows the models to get away with anything they like, because if we've got no data, we can't constrain the model. And so Old Weather is an attempt to solve that by going back into all sorts of records and finding weather data. And in particular, we started off looking at Royal Naval logs from 1890 to the end of the First World War. And it turns out that in the Navy, the weather is recorded on board every ship every 4 hours, come hell or high water. In the middle of a battle, or whether they're in dock, they record the weather. And this is great, partly because ships travel, so this is a worldwide data set, but also because it turns out that the weather at sea is slightly more stable than it is on land. So if you take a measurement in one place at sea, it can be applied to a larger area than you can if you do that on land, because you don't have to worry about hills and valleys and all the local circumstances that make weather here interesting. And so we put these logs on the website, and we said this is an attempt to help Met Office scientists solve the problems of climate, come rescue our weather observations. And the community responded brilliantly. We quickly digitized more than 1 million logbook pages. That data's gone to the Met Office, it's been checked, cross-correlated with other sources, proved to be accurate, and passed off to the international repositories for climate data so that anyone in the world can check their computer models against this data set, which is really exciting. But these logs didn't just have weather observations in. These are the ship's logs. And so weather quickly mutated from being a climate project. In fact, the principal investigator, a guy called Philip Brohan at the Met Office, would tell you that he thinks he's the only person left who thinks of this as a climate project. It quickly mutated to being a history project because there are all these annotations down the sides of the log. So I have two examples that I want to give you as a sense of how this works. One is the Spanish flu. We went actually a little past the end of the First World War. And this is one of our moderators, Janet Jaguar, who we've got to know. She's actually been flown to conferences by the Old Weather team to give her perspective. And so she's been following a ship called HMS Torch. And here she says, okay, it's contracted the Spanish flu on 23rd of October 1918. They're in Edinburgh. And then you see what she's noticed is that the sick list goes from 0 to 3 to 11 to 18 plus 9 in hospital. After putting many on the sick list, they aired the bedding, aired the duffel coats, which is always crucial, down the bedding and went on a route march. I'm not sure why they go, because the Royal Navy believes in getting their sailors out of the ships and out into fresh air, which isn't bad reasoning. So we have a bit of social history, but we also have numbers here. And the community of old weather volunteers self-organized to start recording these sick list numbers. No one actually knew that these logs contained that information. And so here across the Royal Naval Fleet, actually, sorry, this is in one particular ship. Here is the number on the sick list, and you can see the flu epidemic. And at this point, something like 83% of people on the ship were on the sick list with the flu. This data set's been passed to researchers. Of course, the ships have been at different places around the world, but we know where they've been. And so you can use this data to work out the worldwide virulence of the Spanish flu. No one knew that this was even a sensible question to ask, but because people were looking at this data set, they got interested, and they started working on it. There's also the fun examples as well. I'm a big fan of this log. This is from a ship called the Mantua. This is just after they've been loading material. And so this is what a typical log looks like. These are weather observations. It's cold, overcast. These are temperature readings, so it's reasonably warm. Sorry, it's not cold, it's overcast. It's reasonably warm. But this is a list of stuff lost overboard. So this is lost overboard. I don't know if you can see this, but it's 6 packets cocoa, which adds up to 50 pounds. So this is a ship that lost 50 pounds of chocolate overboard just before leaving port. Now, this inspired much sadness in the old weather community and some poetry as well. So we now have an elegy in favour of the chocolate of the Mantua. Now, this is a silly example, perhaps, but I think it's critical in understanding the power of citizen science, because the point is that as well as doing the routine classification, we have that human ability to be distracted, which is extremely useful. We're very good, because of the way we've evolved, at doing routine tasks and then going, actually, for this one, there's something unusual. And in all of our projects, we've often seen that sort of behavior. And in fact, in some projects, it's absolutely necessary. Another wildlife project, as an astronomer, it's wonderful, by the way, to put images of animals throughout my presentation. It's a huge advantage. These are images from a set of camera traps, motion-sensitive cameras spread across the Serengeti in what is the largest network of its type. And if you go to snapshotserengeti.org, you'll be asked to classify these images. And the point here is that some of them are reasonably easy. This is clearly an elephant. Even an astronomer can tell that. This is a buffalo. This is some sort of gazelle. I think it's a Thompson's gazelle, but I've got it wrong before, so I'm not going to go that far. The correct answer to this one is, of course, that these are humans, although this would be difficult for machine learning. And if you're interested in these animals, then I suspect there's a reasonable chance that we could get enough data to train a machine to recognize these things. We've had a go, we're not there yet. But as you build up larger training sets, machines can begin to take on the burden of common classification. But if you're a researcher interested in this thing, this is a zorilla. How many of you have heard of a Zorilla before today? No one? I've mentioned Zorillas a lot in the last 6 months in talks, and so far I've had 2 people, both of whom had been on Snapshot Serengeti. So it's a small skunky raccoon-like thing, to an astronomer at least. They turn up in 1 in 3 million images captured by these camera traps. And so if you're a Zorilla researcher, you are never going to get a large enough training set of these images to be able to train a machine to do this properly. But you are all now trained Zorilla researchers. And at least in 6 months' time, if you see one of these things, you'll remember it's the stripy thing that Chris was going on about and be able to act on that information. If you see one in the street, I don't think you should call me, but if you see one on Snapshot Serengeti, then you've been very lucky. And wherever you look in science, there are Zorillas. In astrophysics, we have unusual, strange bursts of radio waves, which we call fast radio bursts, that are happening around the sky, but only 16 of them have ever been recorded. Only 16 of them have ever been published, which may or may not be the same thing. We're never going to get a training set for those, but we desperately want to find them. They're our Zorillas, and we're going to need people looking at the data to be able to find these unusual things. And in fact, we've discovered that our volunteers can go a lot further than just clicking on buttons and doing what we tell them. And I have 3 examples, but you get to choose. So if you go and vote, I can tell you about advanced volunteers by talking about unusual planets, by talking about Yellowstone-style geysers on Mars, or, one for the ConSciComm crowd, talking about 19th century journals. So please vote. I need some theme music. Next time, Royal Society, we need theme music for this. Also, it's Mars versus journals. So A is unusual planets, B is Martian geysers, and C is 19th century journals. You're doing this deliberately. I'm going to count down. I'm not going to look. I'm going to count down. 5, 4, 3, 2, 1. And it was Martian geysers. Sorry, Sally. No, not when I said. When I said no, it was not. So we're going to talk about Martian geysers. If I get time, you can ask a question. Well, the nice thing about this is I'm preloading questions into the audience with talk slides. So Martian geysers. So we have a project called Planet 4. Planet 4 is about Mars, and it uses data from a spacecraft called the Mars Reconnaissance Orbiter, which has a camera called HiRISE, which is the most powerful high-resolution camera ever flown outside of the Earth-Moon system. So HiRISE is powerful enough that if it took an image somehow without the ceiling of this building, it would detect this desk. It may well be able to see me. It's an incredible piece of kit, and it's mapping the surface of Mars in unprecedented detail. And mostly, you hear about HiRISE when NASA discovers water on Mars again, which is something that happens around this time of year when they need more funding. But mostly the point of HiRISE is to find the places on Mars which are Earth-like, temperate, maybe have or had water, are candidates for future missions. So one of the reasons the Curiosity rover that's currently wandering around the Martian surface was able to land where it did was because HiRISE had already surveyed the area and done hazard avoidance, essentially, and pointed out where the boulders were. However, the team we work with wants to look at Mars because it's Martian, not because it's Earth-like. One of the reasons you study other planets is because you want to find things that happen there that don't happen on Earth, because they're the things that stretch your theories of how planets behave and how planets work. And the most Martian place, I think, on Mars is the South Pole. And when you look at the South Pole with HiRISE, it initially looks fairly unprepossessing. You're looking at a desert region. Obviously, it hasn't rained there for billions of years, if ever. And it's very dry and it's very cold. But once you get your eye in, you can start to see there are features on these images. And in fact, this is one place on the Martian surface over the course of about half a Martian year. So this is spring to autumn. And so what you can see are 2 sets of things. One is what were originally called spiders on Mars. It's not quite as good as the aliens you could have had earlier, but spiders on Mars. Should have put that on the slide for voting, and then you would all be disappointed. So these features here, these web-like features are called spiders. Actually, the journal wouldn't let the researchers get away with calling them spiders. They're called arachnoid form features, or AFFs for short. So these are arachnoid features, and they're sort of cracks in the surface. But then, I don't know if you can see that these dark fan shapes appear over the course of the year and then disappear again. And what we think is happening is that there is ice underneath the surface here. As Mars enters spring, this region of the planet warms up. It gets heated. That ice gets heated, and it explodes out from under the surface with quite a lot of force. It's a geyser-like, I think Yellowstone is probably the closest but not very good Earth analogy, Earth analog rather. And so that material sprays up from under the surface, certainly not somewhere you'd want to be standing at this time of year, and it deposits material in these fans. And so Planet 4 tries to answer two questions. One is that what's actually happening? Is that a good explanation for where these spiders and these fans are? And secondly, because we think these fans are material that sprays up and then is blown by the wind, we can use them to map the winds on Mars. So we get a map covering the whole southern pole of the Martian wind speed and direction. So we can start to understand Mars's radically different atmosphere. So this has been going on for a few years now. Where are we? As of this morning, we'd had 135,000 people classifying nearly 5 million images. And the first papers using that data set have now been submitted to journals. So that's very exciting. This is sort of a medium-sized Zooniverse project. But on the forums where people discuss what they've been seeing, there's an exchange that took place just a month or so ago. It's one of our volunteers, and I'm sorry this is blurry, but he posts this unprepossessing image, and he tagged it and he said spiders. He thinks he sees some of those spider features hidden in here. And one of our scientists said, actually, I don't think I see spiders. I think this is just due to aeolian processes, but just due to wind blowing across the dunes. Fair enough. Except that this person, this classifier, who is not a scientist, who in fact a few months earlier hadn't been interested in astronomy, says, well, actually, I've been to the NASA site, and I've gone and got all the context images. So here's that whole region in context. And what you could see is that, yes, there's wind features here, but my image was down in this region, and you could see that in context you could see what's going on. And it's clear that there's some relation between what's going on the plane with what's going on up on the hills, and that this hasn't been seen before. I'm just going to put the image up because this discussion, I know you can't read that discussion, or at least I can't. And so what's happened here is we've gone from a routine task to somebody asking a question about what they've seen, to scientists getting involved in the discussion, to, we heard this morning, that it's likely that the HiRISE team are going to redirect their camera at this region. So a spacecraft around Mars is being targeted by a volunteer on one of our projects. And it was wonderful to send that email that says, by the way, you know that conversation you were having? We're now going to retarget our best camera orbiting Mars. So I think this is very exciting, and it builds on a long Martian tradition, actually. There's a website, not one of ours, called unmannedspaceflight.com, which I highly recommend if you don't know it, which is a bunch of mostly graphic artists and image processing experts who for the last 10 years have been taking the images that NASA release from their probes and creating beautiful, interesting things with them. So for example, this is an image of NASA's Spirit rover on top of Husband Hill. It spent a couple of years, I think, climbing up to the top of this hill. And this mosaic you see absolutely everywhere. It was on the cover of magazines, it was on the New York Times as the iconic image of this rover's mission. But it was created by volunteers on unmannedspaceflight.com. And they've got to the point where they're discussing, as our volunteers are, with scientists, where they should point their cameras on robots on Mars. So this sort of planetary exploration has now become a participatory, open endeavor. I think that's really, it's a consequence of open data, it's a consequence of providing a way in. You've got to have the simple task so that people feel confident to do that. I have to skip over the 19th century journals. Yeah, I know. So, the other message that I want you to take away is that we can build systems that allow this sort of advanced work. So, scientists need your help. the general public are willing and able to give that help. We can make serendipitous discoveries, and this sort of advanced work matters. And in fact, we've done lots of things to try and encourage it. However, that proves to be difficult because there's a vocabulary to be acquired if you want to go beyond the simple task. So for example, this is the graph of brightness versus time for a particular star, studied in our Planet Hunters project, which has discovered planets and perhaps, although not likely, aliens. And I don't know if you can see, but this volunteer down here has just said, an obvious G door. And this is a piece of technical vocabulary that they've learnt. It stands for gamma Doradus variables. It's a type of star. The star's actually pulsing, which is causing these brightness changes in this particular pattern. But if you come in as a new volunteer, this isn't a very helpful comment. Right? This is like walking into a club and discovering that they're all talking a language you don't understand. Or I went to my first American football game 2 weeks ago, and I still have no idea what happened. Mainly because the attempts to explain it to me used language that I didn't understand. I think we won, but I'm not sure. And so we started thinking about how to do this. Well, I could come in as a scientist and explain, but that's rather like me wandering over to your table in the pub and saying, excuse me, I know lots about what you're talking about, let me put you right, and then disappearing again. It might be effective communication, but it's not friendly, and it doesn't encourage you to think more. So we built Zoonibot. So Zoonibot is a robot that exists on the Planet Hunters forum, and Zoonibot will come in and say, I see you've mentioned G-door. The people who built me think that for some reason you'd want to know this was called this, and I suppose I better give you a link to Wikipedia. Here it is. This is a drawing of Zoobot made by the daughter of one of our volunteers. So we've adopted this as a sort of an Einsteinian robot. I'm not really sure why, with tattoos, it's not really clear what's going on, but nonetheless, this has proved very effective. It's much nicer to have a cartoon robot explain things to you than an Oxford professor. Sad, but true. The place where this really falls down, though, is in the literature, because the goal of Zooniverse projects is to produce papers, right? People get involved because they want to contribute to science. Our tokens by which we show that you've contributed to science is that we publish a paper. We offer this star, you can't see the footnote, links to the full author list of about 300,000 people who've contributed to this particular paper. And we know that our volunteers go and download these papers. They're freely available on services like Archive, but several of the journals, including Oxford University Press, also make Zooniverse papers open access, so that anyone in the world can get hold of them the moment they're published, which is very nice. But we also know that our volunteers struggle with the scientific literature. Reading a paper is hard. They're mostly badly written. Even, not mine, obviously, but most people's papers are really badly written. And even the ones that are well written are written in a kind of scientific jargon. We've also discovered that our volunteers don't know the great secret, which is that you don't read a paper and expect to understand all of it. In fact, you shouldn't read the paper from beginning to end at all. What you do is look at the pictures, look at the figures, decide whether it's worth reading the paper, and then skip over bits. This is how we all do it, but you need to be a confident scientist to do that. And so I think it's worth thinking about. One of the things we're working on, and I thought it tied to today's conference, is how to provide other ways in. And so there's some really nice examples out there. The British Medical Journal, this is a paper that was fairly randomly selected, have not just the scientific paper, but they have 6 bullet points. 3 things that explain what was already known on the topic, and 3 things which explain what this study adds. I think this is great. Anyone can understand this. It's surprisingly hard to do, scientists in the room. I went back and tried to write this section for my papers, and it's not easy. What exactly did your study add to what we know? It's not clear. But providing this sort of information can help bridge this gap between citizen scientists and scientists, and that means we can get more of this advanced work. We also have people offering translation services for us. This is a website called astrobytes.org, which I also recommend. This is a site by PhD students writing up popular descriptions of research papers that have just come out at the level of sort of a starting undergrad. And so these are PhD students learning to write, getting experience of writing, but also explaining what cutting-edge science is really doing. And this site is hugely popular, not just with its target audience of undergrads, but with all sorts of people who are interested in the literature. So more stepping stones are needed. But if we provide them, we know that people will begin to take them. And we're going to have to do that. The next generation of telescopes is going to overwhelm us. Top left is the design for something called the Large Synoptic Survey Telescope, LSST. I've started to think of it as a large, slightly stubby telescope, because that's what it is. LSST is as big as the biggest telescopes in the world today, but it's going to survey the whole sky every 3 nights. So that will produce 30 terabytes of image data every night, with plenty of Zorillas in there. In fact, if you subscribed to alerts for LSST, if I set my phone up to tell me whenever LSST says something has changed in the sky, I would get 3 million text messages a night. And some of those will be routine, and some of those will be sortable by humans, and some of them will need human intervention and citizen scientists, not only to classify them, but to make decisions about which ones should be followed up. And if that's not scary enough, the square kilometre array, the sort of the radio equivalent, which will carpet large swathes of southern Africa and Western Australia with radio receivers, the SKA, which will come online in about 10 years' time, will give us data that matches today's current global internet traffic. And we literally don't know what will be hidden in that data set, but we do know we're going to need all of your help to try and find out. Thank you very much.
So thank you, Chris, for a fantastic lecture, really stunning, amazing stuff. Over to you for questions now, and we've got a few minutes over. Yes.
There's a mic coming, I think. So.
Thank you very much. It was very interesting. I'm Heider Rida from Bain & Company. My question was, how can you use incentives to bring this to the next level of scale? Because I've seen many people on the tube playing Angry Birds. Unfortunately, I haven't seen that many contributing to any of these great projects. And the incentives a game like that provides are actually fake incentives, because, okay, you're the best, but what does it give you? Nothing. So is there a way to bring an incentives angle to this, which would make hundreds of thousands of people be involved? And a side question is, what is the most successful one of all these projects in the number of users that have contributed?
Sure.
Thank you very much.
All right, so the most successful is, in terms of amount of work done, is Galaxy Zoo, but it's been around the longest. It's about 600,000 registered users. The total Zooniverse has 1.4 million. The gamification question is an interesting one. It's clear that that works. People have done it well and people have done it badly. Turns out making a game is really hard. There's one Candy Crush and a litter of failed startups trying to match them. But we've actually taken a strong position against gamification. And let me tell you why. We're trying to do 2 things here. One is to get the work done. The other is to transform how people think of science. I want science to be something that you do on the tube rather than something that's done by people like me in a university. And the research that we've done shows that gamification changes that. When you create an incentive structure that works, people think of the incentives and not about why else they're doing this or why else they're contributing. So it's effective, but it shifts attitudes. There's also some work by a researcher called Alexandra Everly from UCL, who discovered that when we introduced gamification, for the users on whom it worked, in other words, the people who were trying to get to the top of the leaderboard, they used words like stressful and upsetting and annoying, and they talked about the project as work instead of play. So it created this very fundamental shift in why they were doing it. And so I think gamification can work, but you have to just go all out and that's what you're doing. Then you're just building a good game that happens to do science. Or you can sit where we are and say, this is a science project and let's talk about the science. And so I think there are 2 stable positions there. An attempt to blur the 2 is unstable. I can talk much more about this afterwards if you want to chat. But it's interesting how often the question comes up, because it seems like the obvious thing to do, but it definitely has costs.
Yes, in the middle. There's a mic just coming your way.
Oh, right. Oh, sorry. Hello.
We have you surrounded.
Yes, every direction. Eileen Magnello. I'm a historian of science at UCL. I wondered if you could say more about your science gossip.
Sure.
And I was wondering if you have a team of people working on all the Victorian journals. Letters to Nature would be a very good way to find, was a way which the Victorians communicate about new ideas.
Sure. Yeah, it's important to realise that for all of these projects we have an expert team who are responsible for coming to us with the problem. In this case, we have various members of the consultative team, but Jeff Belknap from Leicester, who's sitting there, has been most involved. Do you want to comment on the specific?
Wondering what journals you use, if you have people using all the journals, all the scientific journals that the Victorians wrote in, or are you using things like Nature, which would be a good way?
The first answer to the question is that we're not using Nature. So what we are using is, well, it started because it came out of the Constructing Scientific Communities project, which is funded by the HRC. We're looking at both natural history periodicals and medical periodicals as kind of two genres of scientific periodicals. So Science Gossip, for the time being, is focusing on natural history periodicals.
Right,
Partly
right.
because the people who are giving us this data set is the Biodiversity Heritage Library, which is about 2 million digitized pages, mostly to do with natural history, but they're also a broad church. Anything really that has a species in it will be included in their data set.
But
I think
Nature would have that.
Yeah, but I think the thing is, once you've built the software, it's easy to try elsewhere. So we have transcription projects with Tate, with the Forger Shakespeare Library, and so if there's a collection of stuff that's useful to you, then please come and talk to us about it, and we can set something up.
Yes, there's a question down here. And then one just next to you.
I was wondering if there are any inclusions and exclusions, because I was thinking about children, because something might be very interesting for children to do, but do you allow children to take part, for example?
We do. We can't include them in our research about what the volunteers are doing. That's harder. But yes, no, so anyone can register. In fact, on Snapshot Serengeti, almost 10% of the usernames, that people only identify by a username and an email address, 10% of the usernames have mom or dad in them. So people are clearly doing, I think Penguin Watch is also very popular with, if you're a kid and an iPad, that's hours of fun, I think. Counting penguins seems very satisfying. So yeah, so I think there are children participating. We've also, some of the most impressive advanced work that I've seen has come from teenagers who are either bored at school or in some cases homeschooled, who are using this as an extension activity and are doing great things. So certainly I have a PhD student at the minute who started off doing Galaxy Zoo when she was at school, which makes me very proud and feel very old.
I just have a question about the users as well, which is how active they are. I mean, what is the core of active users? So of the 600,000, what percentage are actually regularly coming back?
Yeah, so
and how long is their kind of life with the project?
Yeah, so let's take the 1.4 million of Zooniverse users rather than just Galaxy Zoo, because I happen to know that. So something like more than 70% of them have come back in the last year, which is pretty good. And the typical pattern is sustained engagement for a short period of time. So somebody will come, will work on the same project 2 or 3 times, or maybe for a couple of weeks, and then they'll disappear. And then something will remind them of the project. So either there'll be something in the news, or we'll send out an email saying there's a new project. And typically what happens when we launch a new project is everyone comes and tries the new project, and then they go back to where they were before. And they have people, when we created the Zooniverse, we hoped for a while that we'd be able to direct attention. You know, crowd, today it's Venus, and then we're going to sort out penguins tomorrow. And that doesn't work. People have a thing that they think of as theirs. About 10% of the users are long-term super users who are there several times a week over a period of at least months. But what's interesting is about half of the classifications come from super users, and the other half come from more casual volunteers. And so to get the work done, we have to cater for both audiences. And I think lots of the projects are designed so that when you go to the site, as I hope you will later on, you can go from not knowing anything to doing something useful in maybe 30 seconds to 2 minutes. I think that's really important, because we need people to fall into these projects and try them before they think too much about the fact they're doing science with a capital S. We have lots of data on this. If you're interested, I can share.
Thank you. I was wondering, there are, as you said, there are many people that are highly effective in identifying galaxies or counting penguins, but what about people who are not so well, not so effective. For example, they don't always spot the penguin, so they can spoil the data. How do you deal with that?
Yeah, so that's obviously something we measure because we want to know how good we are collectively as well. So what happens at the minute is that people who aren't very good at we can show you data that shows that people who aren't very good at a project leave. Like, it's an unsatisfying experience. So people, which is somewhat reassuring because at least people know whether they're any good or not and whether they're getting an experience. So what we've just got a grant to do, though, is to be much more sophisticated. In that if I can tell that you're struggling, what I should be doing is giving you more examples. And so the system will start to learn and respond to people in that sort of way. However, that's the easy bit. Detecting whether you're any good is just a case of keeping track of what answers you're giving us. So did you get this galaxy right? Did you get that galaxy right? And so on. And then training you is usually a matter of just giving you feedback. Actually, that should have been a spiral. But what we want to do as well is measure people's confidence. So we're working with linguists and with those other people to try and understand not just how good you are, but how confident you are. Because the kind of feedback you give somebody who is terrible but confident, Alex, keep trying, but for God's sake, go and read the manual, is very different from the feedback you give somebody who is less confident and still no good. So Sally, I think what you've done is fantastic. I think maybe you'd learn by talking to others or whatever. So the fact there are people in this system makes it incredibly complicated. And as an astronomer, I've learned that galaxies are simple and that getting this sort of feedback right is critical. But we're working on it because we're going to need that when we get to these larger data sets. We're not going to be able to be unsophisticated. So it's a great question and the subject of much work.
Can I ask a
Sure.
question? Have you been able to unpick anything interesting about which parts of the world are most interested in which particular problems, and have you had any surprises about which countries are...
Yeah, we've had lots of low-level surprises. The site gets busy occasionally, and for example, we discovered that our lunar, we had a project mapping the moon, which featured in a week of television specials in South America, which we didn't know was happening. So we've had sort of that low-level surprise. We haven't actually split out our user statistics globally, though. One thing we do know is that translating the sites is hugely important. And so we got phone calls early on in Galaxy Zoo from a bunch of Polish amateur astronomers who basically blackmailed me and said that unless we allowed them to translate the site into Polish, they were going to set up their own site and try and put us out of business. So we gave in, and they provided translation. But they were just having the site in Polish made it hugely effective, and 10% of Galaxy Zoo classifications come from Poland, or at least come from people using the Polish interface. And so that taught us something, and so we've just started crowdsourcing our translations as well. So we now have Mandarin versions of lots of the sites, and Spanish and so on, and that's proving very effective at spreading us around the world. Until now, we've been about a third Europe and about a third US and a third everyone else. But worldwide coverage helps for projects where there's live response. Because if I need to decide now whether to follow up on something with a telescope, I need people who are awake and online at that time. So the more we spread, the better our coverage is.
Fantastic. Well, we need to wrap this up. We seldom have such a stellar performer as you, Chris. This has been a fantastic evening and a great lecture. Thank you very much. Perhaps we could all join me in thanking Chris one more time.
Thank you. Cheers. Thanks. I think the multiple choice worked quite well.